Okay, so here we have a problem about minimizing the cost of the material for a box. Okay, so let's read it. It says, you need to construct an open-top rectangular box with a square base that must hold a volume of exactly 475 cubic centimeters. The material for the base of the box costs 6 cents per centimeter squared, and the material for the sides of the box costs 5 cents per square centimeter. Okay, so they want us to find the dimensions for the box that will minimize the cost of the materials used. Okay, so we need to find these dimensions. So let's first draw a picture. I like to draw a picture whenever possible. So we have a box. Here we go. Okay, so there's the box. Now it says that it has a square base, okay? So that means that the dimensions here are the same. So let's just label them x. And then it has some height, so let's just label that another variable y. Doesn't matter what variables you use, of course, just pick something that looks nice. Now let's see what we have here. It says that the... well, what do we want to do? We want to minimize the cost. All right, so that's the first thing I look for in a problem like this. What do we really want to do here? Well, found it, minimize the cost. So let's write that down. How do I compute the cost of this box? So I know that the cost is going to depend on the size of the box. So it's going to depend on x and y. All right, so let's see. The material for the base of the box costs 6 cents per centimeter square. All right, so let's compute the square centimeters of the base. Well, the base is just a square with dimensions x and x, so the area of the base is x squared, and if I multiply that by 6, I get the cost of the base of the box. Add to that the cost of the sides of the box. Well, what's the dimension of a side of the box? Well, it's x and y, so the area is x times y. But there are 4 sides. So the area of all the sides is 4xy. Now, each side costs 5 cents per centimeter squared. So I'm going to multiply that by 5. So here's my cost function. I have 6x squared plus 20xy. So that's how I compute the cost of the box. Okay. Let's see, what else do we know here? We want to minimize this, but we actually have a constraint in this problem. If we look up here, it says that the box must hold a volume of exactly 475 cubic centimeters. So we can't build just any box. We have to build a box that is subject to this constraint. Its volume has to be exactly this. So let's write that down. Okay, so how do we compute the volume of this box? Well, that is also going to be a function of x and y. Okay, and the volume of a box is always length times width times height. So it's going to be x squared times y. And we're being told that the volume has to be fixed. It has to be equal to 475 cubic centimeters. Okay, so it is just, this is actually our constraint. So what we want to do here is we want to minimize this, our cost, subject to a constraint. What is our constraint? It's this equation here. So we want to minimize this expression subject to this constraint. And whenever you want to minimize something subject to a constraint, you want to use the method of Lagrange multipliers. Okay, so that's what we'll be doing here. Lagrange multipliers. All right, well, Lagrange multipliers says that when you want to minimize a function subject to a constraint, the minimum will occur where the gradient vector of the function is parallel to the gradient vector of the constraint expression. Okay? So, in other words, all we're doing is finding where the gradient of the cost function is parallel to, so that means is a multiple of, I'm going to multiply it by k, parallel to the gradient of the constraint function. That's all Lagrange multipliers is. We're just trying to find where does this happen. You can choose whatever letter you want for this. It's just a letter that denotes the fact that these two vectors are going to be parallel, so they have to be scalar multiples of one another. So that's all we have to do here. We just have to find where does this happen. Okay, so let's compute what gradient of C is. Well, the gradient of C, I'm going to take the x derivative of this. All right, that's going to be 12x plus 20y. Then I take the y derivative of this. That's just 20x. That's the gradient of Z. What's the gradient of V? Gradient of V, I'm going to take the x derivative of this. That's just 2xy. Then I'm going to take the y derivative of this. That's just x squared. And I set these, I write down this equation here. Okay, so that means that the first components have to be related like this. So I know that 12x plus 20y is going to equal k times 2xy, or in other words, 2k xy. And then the second components are going to be related like that. So I got 20x is equal to k times x squared. Okay? So what I have here is I have a system of equations. But how many unknowns do I have? I have x, y, and k. So, oh no, I have three unknowns, but only two equations. If you have three unknowns, you want to have three equations to be able to solve it. I need to find a third equation somewhere. Well, I have one we haven't really used yet. That's the constraint equation itself, right here. This is an equation. So we can add this to our list. All right, so I'm going to add that in here. X squared y equals 475. So this here is a system of equations. Three equations, three unknowns, and we want to solve this. So the goal of this problem is just to solve solve this system. I'll post that in another video.